Hello, I'm an academic from Griffith University. I typically teach analytical chemistry, but this summer I want to reteach myself organic chemistry. Seeing as it helps me learn, I thought I'd record my progress with these videos. Today we're going to be talking about molecular orbital diagrams and what they can tell us about organic chemistry. So this is a molecular orbital diagram, and it allows us to understand certain forms of chemical bonding. Looking at what they show us, you can see there are two atomic orbitals on either side, and they combine together to give us the molecular orbitals for those two atoms. In this case, the atomic orbitals are two atoms of hydrogen, and the molecule is the H2 hydrogen molecule. The atomic orbitals themselves typically are focused on the valence shell of that atom, like the 1s, 2s, 2p, and so on. The scale provided shows some indication of the energy of those orbitals, as well as the combined molecular orbitals below. Typically when molecular orbitals are taught at university, they're taught for simple diatomic molecules like H2, N2, O2, because it quickly becomes quite convoluted when you're dealing with more complicated molecules. However, in organic chemistry, we can use these to think about the formation of bonds between two atoms, or even the breaking of bonds between two atoms. The first thing to consider is when you're combining any number of orbitals, it's going to create that same number of new orbitals. So here we have two lots of 1s orbitals, one for each hydrogen atom, and consequently we're creating two new molecular orbitals. One here, a bonding orbital, and a second anti-bonding orbital. To combine atomic orbitals together, they need to have similar energies and they need to have matching symmetry. Here we're combining two atomic orbitals that have exactly the same energy, and unlike p orbitals, s orbitals are essentially spherical and directionless. So provided those atoms come together, there is going to be an overlap of their symmetry. We can see that each atomic orbital here has a single electron within it. So for two hydrogen atoms, we have two electrons. When we're filling up our molecular orbitals, we need to start at the lowest energy orbital and fill from the bottom, being aware that each of these orbitals can hold a maximum of 2 electrons. So this principle of filling the lowest orbital first is called the Aufbau principle. And whenever you're adding an electron to an orbital, the first electron will be spin up, shown here as an upward arrow. This spin up, spin down relates to the angular momentum of the electron, which is essentially a quantum state, and electrons cannot share the same quantum state. So the first electron that goes in is spin up, but the next one needs to then be spin down. You can't have two spin up electrons sharing the same orbital or two spin down electrons sharing the same orbital. And this idea is the Pauli exclusion principle. Now the last thing we need to consider when we're filling up molecular orbitals is that if two orbitals have identical energy, we need to place a single electron in each orbital before we start doubling them up. And like we said before, first electrons we apply are going to be spin up. So that's a combination of Hund's rule combined with the Pauli exclusion principle. So here's an example of a molecular orbital diagram for O2, the oxygen molecule, made by combining two atoms of oxygen. So the atomic orbitals are shown here at the side. So just looking at one of the orbitals of an oxygen that's going to make up the O2 molecule, we can see that oxygen has 6 valence electrons. 2 here in the 2s orbital and 4 in the p orbitals. And that's the same on the opposite side. Combining those together, that means we have 12 electrons to place inside the O2 molecular orbitals. Now, following the Aufbau principle, we start at the bottom, lowest energy orbitals, and move upwards. 2 in the 2s sigma bonding orbital, 2 in the 2s sigma anti-bonding orbital, 2, 4, 6 electrons in the sigma and pi bonding orbitals from combining the 2p orbitals, and that leaves us with 2 left over, which we're going to place in the anti-bonding orbitals. Now the oxygen molecule is a little bit unique in that the 2 pi anti-bonding orbitals are equal in energy. So following Hund's rule, we would add 1 electron each to these anti-bonding orbitals that have the same energy. And according to the Pauli exclusion principle, we're going to make sure that both of these electrons are spin up. And that gives us our 12 electrons in our central molecular orbitals. And so considering the p orbitals, what we would expect molecular oxygen to have is a single, double, triple bond, but there are 2 anti-bonding electrons. So we lower that down to a double bond, which is how we would draw the oxygen molecule. Now, this molecular orbital diagram actually shows us why oxygen behaves in unusual ways. First, you might have heard of oxygen being described as triplet oxygen, and that comes down to these 2 unpaired electrons. Thinking about the quantum states of those electrons, you could get spin up, you could get spin down, and you could get spin up and spin down. And those 3 states are what give it its triplet name. Next, because it has unpaired electrons, it's paramagnetic. And indeed, if you were to place some liquid oxygen around a strong magnet, it will be attracted to the magnetic fields. An electron. And lastly, it gives us an indication as to why oxygen is so reactive. It's arguably the most reactive chemical that we know in chemistry, and it comes down to this fact that it has 2 unpaired electrons, so it basically behaves like a diradical species. So we can kind of think about the bonding of oxygen in this way. We have one bonding sigma bond, shown here in red, and then we have 2 pi bonds, each of which has 2 bonding electrons, but also a single anti-bonding electron, cancelling out 50% of the bond strength. So unlike a carbon double bond, where you would typically have 2 electrons in a sigma bond and 2 electrons in a pi bonding orbital, oxygen's a bit different in that it has 2 bonding pi orbitals, but they're only at 50% strength, giving each some radical character. If we go back to the hydrogen molecule and were to consider the energies of the bonding and anti-bonding orbitals, you would see that this energy here to go up to the anti-bonding orbital is actually greater than the energy decrease that you observe to create the bonding orbital. And this comes down to the orbitals being in phase when they are bonding, but they're actually out of phase when they are anti-bonding. And if those orbitals become out of phase, they have a repulsive effect, which adds a little bit of energy to the anti-bonding orbitals. Now, so far I've only considered overlapping between identical atomic orbitals. But in organic chemistry, we typically see bonds between carbons and nitrogens, carbon and oxygen, carbon and silicon. So we know that bonds can form between different elements. Now, the strength of a chemical bond relates in part to how similar in energy the atomic orbitals are. And 2 atoms of the same type will typically have the closest energies together. So we can compare this bond between an sp3 carbon and another sp3 carbon that have equivalent energy, and then look at the same sp3 carbon, but this time we're looking at an sp3 silicon, which is beneath carbon in the periodic table. And we can see that the energy levels of the atomic orbitals are now mismatched. Because of that, when we combine them to give the molecular orbitals, the lowering in energy of combining them is less than if you were combining the same types of atomic orbitals together. So comparing these 2 molecular orbitals, you can see that a carbon-carbon bond is going to be stronger than a carbon to silicon bond. Because to break these bonds, what we need is to elevate one of these bonding electrons up into the anti-bonding orbital, thereby cancelling out the bond. And the energy jump for the carbon-carbon bond is great, while the energy jump for the carbon-silicon bond is comparatively smaller. So this would require less energy to promote an electron from a bonding orbital up here into an anti-bonding orbital, thereby cancelling out that bond. So these examples are for sigma bonds, but there's even more of an effect if you look at the pi bonds. So a carbon-carbon pi bond, 65 kilocal per mole, but when we look at the carbon to silicon bond, it's almost halved, down to 36 kilocal per mole. Now, the types of elements are also going to factor into the bond strength. So focusing on a silicon to silicon bond, which we might expect to be strong because they're identical atoms, this is actually the weakest of the 3. And this is because silicon is a much bigger atom. Instead of dealing with the 2p orbitals, we'll be dealing with the 3p orbitals, which are further out from the atomic radius and so are weaker. So one trend to think about is if you're considering the 2 atomic orbitals and they are not the same atom, The greater the difference in electronegativity between those two atoms, the less strong the bond is going to be. So this graph shows you the electron probability in the various atomic orbitals in relation to the distance of those orbitals from the nucleus of the atom. So if we imagine 0, we're sitting at the nucleus of the atom, and then as we move outwards, we're going to encounter different atomic orbitals. So the first orbital you'd encounter is the 1s orbital, as you would expect. This is spherical in nature, and it's held close to the atomic core. Moving further out, we encounter the 2p atomic orbital. It has this two-lobed shape, like so, and you can see that the orbital has two phases. So the electrons can exist on either side, but we can consider one half to be positive, the other half to be negative. Even though this isn't like formal positive and negative charges that we think about in chemistry, and it's not really like spin up, spin down either. Instead, it's a quantum property. There are 3 p orbitals, each which can fit 2 electrons, giving you a maximum of 6 electrons in the 2p orbitals. Those orbitals align to the x, y, and z axes. Moving further out, the next one you encounter is the 2s orbital, and you can see it has sort of 2 lobes shown here, or there's a node whereby there is 0 electron density and 2 regions otherwise where the electron could be. These 2 regions actually have a different phase. So for instance, you can consider this to be a positive region and this to be a negative region. And again, only 2 electrons exist in the s orbitals. There are other orbitals moving outwards, but we're just going to focus on the 1s, the 2p, and the 2s orbitals for now. So one interesting factor about the 2s and the 3s orbitals are that they are more exposed to incoming atoms than their corresponding p orbitals. So for example, if we imagine an incoming atom moving in this direction, and our first atom is sitting here at 0, as the atom moves in, first orbital they're going to potentially encounter is this 2s orbital before the 2p orbital, which is closer to the atomic nucleus. And so for that reason, we can imagine that this carbon has several p orbitals associated with the triple bond, but also an s orbital associated with this hydrogen. So if we imagine a base coming in from this direction, it can interact with the s orbitals before interacting with the p orbitals, and you can get this abstraction of the proton, which gives some chemicals more s character and chemistry that reflects that. So for a quick reminder on hybridizing orbitals, in many instances the atomic orbitals don't actually reflect these idealized s and p orbitals. Instead, they hybridize together to give you hybridized orbitals. Sticking with carbon, if carbon is bonding to 4 atoms, that means that 1, 2, 3, 4 orbitals are going to be hybridized to give 4 sp3 orbitals. And to create an sp orbital, we take our s orbital, we overlay it over the top of our p orbital, and wherever the phase of the electrons overlap, they constructively interfere. So if we imagine the dark coloured aspects of these orbitals are negative and the light coloured parts are positive, the s and the p dark regions overlap and get larger to give you this orbital here, while the p orbital shrinks and gets smaller. Now considering this would be the 2s orbital and these are 2p orbitals in this example, if we go back and have a look, remember that the 2s orbital actually has a small positive lobe and then a large negative lobe. So when you overlap a 2s orbital and 2p orbital, it doesn't completely cancel out the positive part. There is a small amount of positive character in the 2s orbital, so there is some retention of that as well. If we consider this carbon bonding only 3 atoms, such as in ethylene, well in this case we're going to have 1, 2, 3 that are hybridized, and then the last one is just going to remain a p orbital. So this is termed sp2 because it's combining 1, 2, 3, spp, sp2. And if we look in the representation, say at this carbon, we can see that there is 1, 2, 3 sp2 hybridized orbitals and our single pristine 2p orbital, which has not been hybridized. We can imagine a molecular orbital diagram for this, where we have our 3 sp2 hybridized orbitals and our single p orbital. Combining those two together, we get one sigma bonding sp2 molecular orbital. So that's the one here in the center. We're not considering 1, 2, 3, 4. And we also get one properly aligned pi bond from the two pz orbitals. And that would be these ones here. So the next thing we should consider is how these molecular orbitals will appear depending on whether they are bonding orbitals or anti-bonding orbitals. So if we combine an s and a p orbital together, that can either form a sigma bonding orbital, where if we imagine the 2s orbital is negative and it aligns with the negative lobe of the 2p orbital, we get overlap of electrons in the same phase and they constructively combine together to give you the bonding orbital. However, for an anti-bonding orbital, we have the 2s orbital, which is negative, but now the positive lobe of the 2p orbital is approaching it. Here we get destructive interference, so effectively it cancels out one another, and no attractive force from this interaction. We can do the same thing when combining a p and another p orbital together. So either the phase of the orbitals will be aligned to constructively combine together, giving you this sigma bond, or they will be misaligned, meaning they combine destructively in an anti-bonding orbital, destabilizing that bond. So this means if we imagine a bonding interaction, like here or here, but the molecule gains enough energy to promote an electron from a bonding to an anti-bonding orbital, well, these stabilizing forces are going to switch over into these anti-bonding destabilizing forces, shown here. And this is effectively what happens when a bond breaks. A bond goes from a bonding orbital to an anti-bonding orbital, and the attractive force holding the atoms together disappears. Now, we've talked about different atoms combining together in molecular orbital diagrams, but the orientation of the orbitals also affects bond strengths. Here we have two orbitals that have matching orientations and strengths, so the lobes that you see are the same size. That's better than if you have misaligned orbitals that have differences in the amount of electron intensity. So the top one's more for sigma bonds, but the same goes for pi bonds as well. Correctly oriented orbitals and orbitals of similar sizes are going to be more stable than incorrectly oriented orbitals or orbitals where the electron density is mismatched. Now, this idea quickly becomes complicated and it requires a holistic view to understand the stability of bonds. And this is largely where computational chemistry comes in. This is not something you can just figure out with a pencil and paper. So I thought I'd give you an example of simple versus truer molecular orbital diagrams. So if you look up the molecular orbital diagram of the nitrogen molecule obtained by combining the atomic orbitals of two nitrogen atoms together, it's a decent model. Nothing here should be really jumping out as being particularly controversial, but the strange thing is you can see that the sigma bond in nitrogen's triple bond is higher in energy than the pi bonding orbitals. And the main reason for that is that when we consider the atomic orbitals, you can see they're listing the 2s and the 2p orbitals. But in fact, we really should be considering hybridized orbitals and combining those in our molecular orbital diagrams. And if you do that first, taking the unhybridized orbitals of nitrogen, hybridizing them first to give you our hybrid orbitals, and then combining the two hybrid orbitals of our atoms together, all of a sudden we can see why the molecular orbitals are arranged the way that they are. While on the left, this is shown as a sigma bonding orbital, over here it's actually an anti-bonding orbital made from combining two hybrid orbitals together. So in this truer model, we have 1 bonding, 2 bonding, 3 bonding, 4 bonding, and 1 anti-bonding orbital, giving us a net triple bond. Whereas over here in the simplified model, we have a bonding and anti-bonding down here for the 2s orbitals, and then a single, double, triple bond associated with the 2p orbitals. But we're left with this weird setup over here, which doesn't seem logical. Whereas the bonding anti-bonding situation on the right explains why it appears the way that it does. So bringing this sort of back to organic chemistry. Chemistry is typically done at the frontier orbitals, which occur at the highest occupied molecular orbital and the lowest unoccupied molecular orbital, so HOMO and LUMO. These orbitals dictate the reactivity and the electronic properties of molecules. If you can map out the HOMO and LUMO interactions, you get a good approximation of how chemicals are going to react. This is because whenever a molecule reacts, bonds form and break, and the molecular orbital diagrams can show this by shifting electrons from a bonding orbital to an anti-bonding orbital, so a HOMO to LUMO transition. So just to give you a very quick example, we have two molecules here, one here, one here. We have an iodine atom, which is a good leaving group in both in a similar situation. The main difference between these two molecules is the location of the lone pair attached to the nitrogen. On the left, the lone pair is oriented downwards, away from the iodine, while on the right, the lone pair is oriented upwards, towards the iodine. Now, if the iodine is going to be acting as a leaving group, the bond keeping the iodine attached to the molecule needs to break. That is, it needs to enter the anti-bonding state. So if we draw that in, we have our anti-bonding interaction here, and we also have our opposing lobe of electron density here. Now in this situation, these two lobes are properly aligned to overlap, and so they are going to stabilize one another. So this lone pair is going to stabilize the anti-bonding state that would release iodine from the molecule. Looking at the other example, the lone pair isn't correctly oriented to stabilize this part of the anti-bonding interaction, or it does to a lesser extent. And so because of that lone pair stabilization, this molecule is more reactive in E2 elimination reactions, because the anti-bonding state is being stabilized, which means the iodine is freer to leave. We can also see the reason why E2 eliminations typically occur in this staggered conformation. Here we have our chlorine leaving group, we have our base coming in to attack one of the hydrogens on the other side of the molecule. We can see that the base specifically is targeting this hydrogen, because the electrons that make up the sigma bond to that hydrogen can be cooperatively transferred into this newly vacated orbital made when the electrons transfer down to the chloride. Another interesting effect coming out of this is hyperconjugation, which is where electrons are delocalized from sigma bonds into properly oriented neighboring orbitals. So here we have a molecule of ethane. Ethane prefers to be in this staggered conformation shown here, and part of that comes down to these electrons making up the sigma bond to this hydrogen partially stabilize the orbital of the neighboring antibonding orbital between carbon and hydrogen. This is even more pronounced in the reaction of carbocations, where we effectively have an empty neighboring orbital adjacent to the electrons making up a sigma bond to some kind of leaving group. Given the orientation is good for overlap between these two orbitals, these electrons can effectively be stolen, creating a double bond and releasing this leaving group, like so. And we can show that in this molecular orbital diagram over here. So to summarize, molecular orbital diagrams offer useful insights into various bonding phenomena. If you're going to combine orbitals in a molecular orbital diagram, they need to have similar energies and orientations. The amount of electron density and the orientation will also influence the bonding strengths within molecules, but is important for explaining reactivity in situations like hyperconjugation and elimination reactions. So that's my quick whirlwind discussion on molecular orbital diagrams. I hope you found it interesting. If so, pop a comment below, since I'm really interested in who actually is going to watch this, if anyone. And also let me know if I've gotten anything wrong, because like I said, I'm trying to reteach myself this stuff. And there's no guarantees I'm going to get it all right. Anyway, that's it. Thanks for watching.